The primary focus of our research is on the eutrophication of the Yahara Lake system in Madison, Wisconsin, which consists of the lakes Mendota, Monona, Waubesa, and Kegonsa. Eutrophication is a very serious problem that leads to the widespread death of aquatic life through the growth of blue-green algae, which both deprives the system of oxygen and releases toxic neurotoxins into the water that have been linked to both ALS and Parkinson's disease. The image you are currently seeing is actually of Lake Kegonsa during the summer of 2018. Clearly, nothing can survive in these waters, so we need to know what eutrophication is and what causes it. Eutrophication is typically caused by excessive amounts of nitrogen and phosphorus being introduced into an aquatic system through the use of fertilizers typically used in both agricultural and urban applications during a significant rainfall event. Our ultimate goal is to predict the amount of phosphorus in the lake after one of these runoff events, so lake management personnel can implement strategies based on different rainfall scenarios. To accomplish this goal, we are creating a model of the lake system through the use of a system of differential equations. Differential equations have several applications in science, engineering, and several other fields. A few examples include the heat equation, which can be used in various settings, such as this heat exchanger typically used in food manufacturing to condense liquids such as milk or whey. Another example is the Black-Scholes equation, which is used to analyze financial markets. Did you notice any similarities? They're essentially the same equation. That is the true power of differential equations. If you use one equation for many different types of applications and draw new conclusions based on information you may find on the equation in another completely different field. For the purposes of our model, we will be using the following equation, which is well known in the field of water science, where P equals the amount of phosphorus in the water, Q is related to the depth of the lake, with values between 2 and 20, with 2 being a very deep lake and 20 being a very shallow lake. R is the maximum recycling rate of phosphorus. M is the concentration of phosphorus when recycling is half its maximum rate. S is the loss due to sedimentation or transport. L is the phosphorus load delivered by watershed and upstream sources. The parameters of our model will be fitted to data from the U.S. Geological Survey, Environmental Protection Agency, and the U.S. Department of Agriculture. This is a map of all the collection sites where water chemistry data, such as oxygen level, nitrogen concentration, phosphorus concentration, and several other chemical readings are taken. Other data is collected at these sites as well, such as CG depth, which measures the clearness of the water. This is actually an image of a CG depth recording performed on Lake Mendota. After collecting all the data, we fit the data to the parameters using a technique called statistical bootstrapping, combined with nonlinear least squares. Samples are taken from our data set with replacement, and nonlinear least squares is run on every sample. In the end, we analyze all the samples and compute confidence intervals for each of the parameters. To accomplish all of this, we are using a statistical programming language commonly used in data science called R, which has a number of data cleansing functions and many other functions that support statistical operations. In the end, we hope to supply lake management personnel with a tool that will hopefully reverse this eutrophication and return the lakes again to their original pristine condition. Thank you very much for your time.